Understanding what parameters or features has what level of impact on a solution to a problem statement is very important. If the talk is about using machine learning to solve a problem, then providing the algorithm with high quality features is what makes the difference between a raw machine learning model and a very well optimized one. Now, feature engineering is the most critical aspect of working with data and helping the machine understand the same. This is a skill that all analysts, data scientists, and even machine learning engineers must possess. Now, keeping exactly this in mind, we here at Great Learning have come up with this course on feature engineering to get you started with the same. I shall also be covering a hands-on demonstration to help concrete your understanding. With that, I know you guys are super excited to start this course. Well, what are we waiting for? My name is Anirudh Rao. Let's get started.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.
So to take a look at the agenda on this course, feature engineering, we have to start this out by understanding and taking a look at what feature engineering even is. Now, this is a term that gets thrown around a lot regardless of you working in data science, data analysis, machine learning, even deep learning to a good extent. So if the world is going gaga over feature engineering, we need to begin by understanding what it is, where it is used, and why we even require this, right? So we're going to cover all of that in the introduction aspect. Now, once we are done with the introduction to feature engineering, we also have to make sure that we have it covered the entire process of how things work, right? Once you know what it is, you'll be curious to understand how it works. So we're going to take a look at how feature engineering works as well. Now, once we are clear with how feature engineering works, we will make sure to take a look at the various techniques that we have in the world today, wherein be it researchers, be it students, or even enterprise grade companies are using some of these techniques to make sure that they have correct features and very well optimized models, right? So we're going to take a look at that. Now, once we understand the various techniques that are out there, it becomes very important for you to understand what a correlation matrix is. Now, a correlation matrix gives you one dashboard kind of a view wherein it talks about all the different features and how they are related to each other. So that's a very, very, very important aspect we are going to cover. Once we understand correlation matrix, we are going to be taking a look at understanding how the model can be tweaked in terms of handling concepts such as underfitting and overfitting too. So we're going to understand what they are, why they cause a problem, how they cause a problem, and how we can go on to handle them as well. Once model performance is done, it's right time to take a look at the demo, which is basically diabetes detection using machine learning. Now, there's a lot of reasons we are considering this very particular demo, because in the introduction, we're going to be trying to understand what feature engineering is by taking a concept or a simple story about diabetes, right? So I hope the agenda that we're covering on this course is clear to each and every one of you all. You might have heard of the term feature engineering previously, right? When you talk about engineering, you are trying to understand how one can go on to create something, how one can go on to take something from being a prototype all the way to being a product, right? When you say, hey, I have engineered a solution to this, you're basically trying to say you've either solved a problem. Now, when we say feature engineering, how are we trying to associate these two things is the question you must be asking yourself. And to answer that, let us actually consider a small story. Now, ladies and gentlemen, you remember I just spoke to you about the demo that we're going to take a look at, wherein we will try to detect and predict the onset of diabetes. Well, let's try to work our way back to actually understand feature engineering using the same concept of diabetes. Now, let's just have a small story here, as in you are a person right now who's willing to understand what are some of the various factors that will cause diabetes, right? Now, diabetes is a very common health condition across the world, right? It isn't caused by any sort of virus, it isn't caused by any sort of bacteria. It's a condition that sets in. There are many factors to it. Now, when I say many factors to diabetes, you will be curious to understand, okay, so if you're saying that there are many reasons of why one might get diabetes, what are these reasons, right? So basically you'll try to do a little more research, and maybe you will give your doctor a call. So you'll call your doctor and you'll ask him or her, saying, what are some of these reasons of why one would get diabetes, and you will understand the factors that will cause the same, right? So for example, you have a conversation with your doctor and your doctor tells you, hey, so diabetes is basically caused by maybe having an unhealthy lifestyle, maybe having a very dormant kind of a lifestyle, and even to a point where you might not be taking care of your sugar intake, right? Because there's only so much that your body can do in terms of how it can handle sugary foods. And we all know that a lot of sugary foods can definitely lead to a type of diabetes as well, right? So it's not only that. There are a lot of things. One main thing that usually comes into the picture is the age factor, right? So when someone is aging, you will see a lot of trend, not just here in India or not just in the United States, but almost everywhere across the world. So when people start aging, that is when they tend to start seeing symptoms of diabetes as well. So if age is one of the criteria, what are the other criterias? I just told you about how maybe having an unhealthy lifestyle may also lead to this, right? So when you say unhealthy lifestyle, if you're eating a lot of sugar, if you're drinking a lot of fizzy drinks, or maybe not watching your intake, you're compromising your body's ability to basically handle all of these extra sugary stuff that you're putting in, right? So there is an indicator, you can find out the blood sugar level, right? So once you find out the blood sugar level, and if it is above a certain threshold, it means that your body is not able to absorb or take care of all of that, and there is something called insulin in your body as well, right? So there are many factors to it. So having an unhealthy lifestyle can lead to obesity, can lead to having a really high body mass index. A body mass index basically talks about how fit a person is based on their height, based on their weight, and a couple of tiny factors as well. So what did we just speak about? We spoke about maybe 3 or 4 reasons of why we think diabetes can be caused, right? First of all, it can be an age criteria. Second of all, it can be due to unmonitored intake of food. The third thing is that it can also be hereditary as well, right? Now, there has been research, concrete research, which says that there's a very good chance that you can have an onset of diabetes if it's in your family line, if it's in your bloodline as well, right? Now, that is one of the other features. Now, are these the only features that will help assess if someone has diabetes or not? Right? There are many things, as I just mentioned. Even for example, things such as stress, right? Stress and strain, your mental health, that can also lead to diabetes as well. So if you're talking about age, if you're talking about fitness, obesity, if you're talking about body mass index, and everything from stress all the way to even blood pressure, right? These are some of the factors that will cause diabetes. Would you guys agree with me? Well, I know you guys will be saying yes to this, because if all of these are some of the metrics that we can track the body mass index on a number. It's a number, right? So if BMI is 25, it means that the person is healthy, fit and active. If it is below 25, I think it's basically malnutrition or something like that. And if it's above 25, 27, 30, 32, it means the person is obese. Now, why is this important for us to understand feature engineering? Well, these are some of the features that you will understand, you will digress to basically help your machine understand the same as well, right? If you just say, hey, I am fit, your computer will not be able to assess and gauge the level of fitness. Maybe you're on your call with a brand new doctor, you say, hey doctor, I am fit. So when you say I am fit, what do you mean? There are so many factors that your level of fitness, the threshold might be very different from an athletic person, right? that can happen. So instead of just saying, hey, I am fit versus I am not fit, all the other criteria that you see, body mass index, insulin level, blood pressure is also a number, age is a number. So you can have all of these numbers, provide these numbers to your machine learning algorithm, get it to understand, get your machine learning algorithm to actually understand what is going on with these numbers. And this is the important part, how the change in these numbers can lead to a person maybe having diabetes or maybe not having diabetes as well, right? This is what we will try to find out. And if you talk about feature engineering, it's basically using each and every one of these things that we use to track, right? An entity which has an understanding and which has an impact on your final solution of how your model understands something. All these entities is basically what we call as features. Now, feature engineering is basically us trying to understand which features may or may not positively contribute to our solution. Now, let's just say hypothetically, let me just quickly go back to the previous slide. Now, let me just say hypothetically, that having a lower age can cause diabetes. Now, that is not true, correct? But we know this. But our machine learning model that we are trying to get it to predict our diabetes onset, it will have no idea how age is related unless you actually provide relevant data, maybe from the past patient data or something like that, from hospital records, so that your machine knows what feature has what amount of impact. Now, let's just say a person is of the age 55, they have very good fitness, they have a very nice body mass index, their insulin is absolutely good, they are not stressed, but they have a very, very high blood pressure problem. Right? Now, when that is the case, you cannot just say, hey, no, this person might not get diabetes because 90% of the features are like normal, but it's just only one tiny feature which is out of whack, right? No, that cannot be said, because you do not know. You, me, anyone untrained in the field of medicine might not know how important having the right blood pressure is. If that number goes out of a threshold, maybe there are many things like Jenga blocks which fall down, which will eventually cause diabetes as well, right? So just writing it off saying everything is normal apart from blood pressure means the person has no diabetes is completely incorrect. Why? Because you do not know what amount of impact that particular feature is having on our entire result, correct? Now, the concept that we'll be discussing later in the course, basically called as correlation matrix, gives you this exact understanding of how two features can be related to each other, right? So we are going to take a look at that as well. So what do you do once you know that, hey, these are some of the features, this is how I can get my machine to probably understand what data looks like and eventually what is the stuff that's present in the data. So at the end of our discussion, even if it is non-technical, would you guys agree at this moment of time that all of these things that we just spoke about, age, BMI, all of these are features? Because they're called features because they have a final say in the result, right? Now, if all of these features were absolutely normal, there is still a chance a person might get diabetes. And if all of these are normal and maybe one or two are out of their threshold, the person still might not have diabetes as well, right? So it becomes very important for us to understand what feature has what impact, and the entire study of us actually going to do this is feature engineering, guys. So now that you have a slight understanding of what feature engineering might be, and I've mentioned machine learning multiple times, right? So you might be curious to understand, hey, so if feature engineering is this important, where do we use it popularly? Feature engineering is super popular in the field of machine learning. Now it forms to be, in my opinion, the most important aspect of machine learning. Because whenever someone comes to you with a problem statement, whenever a client, whenever your manager, or whenever someone says, hey, I want you to use machine learning to solve this particular problem that I have. When that happens, you'll have to first of all find out how you can train the machine learning algorithm to do the task for you. What is the data that you can send to your machine learning algorithm? And not only that, what are some of the things which will positively have a correlation? What is some of the things that will affect your result? In our case, we saw so many things. We saw age, we saw body mass index, we saw blood pressure, we saw stress, right? So there are many things which you will understand. And of course, some of those features might not even have a large impact on the final result as well. I'll give you a very small example. Think of the situation wherein you're trying to buy a new home. So you're trying to assess and analyze what are some of the prices in those particular areas, and you will know wherever you are at any part of the world, you will know that there are certain parts of your city where maybe owning a home is going to be very, very, very expensive, right? Many reasons for that, of course. So of course, here in Bengaluru as well, where I'm from, we have multiple places such as that, multiple areas wherein the cost for the land is super high. Now, why is the cost for the land super high there? Maybe better amenities, maybe fantastic access to schools and shopping malls nearby, maybe it's a gated community which provides amazing security, or maybe for the fact that the crime rate in that area is very low, or it's 100% residential and no commercial properties there. So when you think about all of these reasons, everything that I just said, don't you think these are features as well? So you guys should come to a concrete understanding by now that even though you might have never used the term feature engineering, you have actually used these concepts in multiple walks of your life to assess what has what kind of an impact, right? When you think about it, that is feature engineering. But the important discussion we are about to have right now is to assess and understand the importance of machine learning and how feature engineering makes it super important to be there, to be present, and to optimize our machine learning algorithms, right? Now, it's very simple. We can manually understand what sort of an effect age and BMI and all of those have on diabetes. But when you're trying to train your machine learning algorithm, if you train it incorrectly, or if you do not provide a very important feature such as maybe blood pressure to it, it will not know there's an underlying factor which is basically causing diabetes. So at the end of the day, it will never be very efficient in giving you a concrete result, right? Think about it. If it doesn't even know that BP causes diabetes, how will it even predict it for you, right? This is where step number one comes into the picture, which is eventually you guys trying to understand, trying to work on the features themselves first. First of all, to feature engineer something, you would list all the features that you think will have an impact on the solution. Once you do that, you would collect past data where you can map what each of the feature was, and at the end of it, you can say, hey, this person maybe had diabetes, this person did not have diabetes, or in fact, if you have patient records like what we will check out in our demo, you can for sure say, hey, this person has diabetes, this person does not have diabetes. Why? Because there's a medical report there. Now, once you know it, you can hide it from your machine learning algorithm, train it, and later test it to see if your feature engineering has worked correctly, right? So it becomes very important. Now, whenever I've spoken about feature engineering, there is one question that I usually get. People say, hey, so if we have really powerful machine learning algorithms, and of course we have many powerful algorithms today. So if we have these really powerful algorithms that are super intelligent, that get the job done, why should we even bother about feature engineering? Well, this is a misconception, because at the end of the day, when you're talking about feature engineering, you have to understand something. Even the most powerful machine learning algorithms that are out there will not be able to do anything unless you actually provide good features. So to wrap it up, what I would like to say is that you can turn a good machine learning algorithm into a great machine learning model just by changing the features. Now, usually there is a situation where beginners are trying to learn feature engineering. They might skip and go ahead to directly understand machine learning. Now here, if you do not know how to tackle different features, you will be breaking your head about understanding why your machine learning algorithm is giving you very low accuracy numbers. Even though you have a very good amount of data, high quality data that you're providing to your machine learning algorithm to basically understand the result, it will never give you an accurate result. You will try to change methods of learning, you will try to change algorithms, you will try to change so many things in the learning process itself, but 90% of the time people overlook the entire aspect of knowing that features are the most powerful governing entities, because they have a direct say into telling you, hey, this is what is the cause for something. Now if you're cutting off that link, Think about it, right? So it becomes very, very, very important, not just for machine learning. I want to add something here as well. It happens even for deep learning too. So for both machine learning and deep learning, where you're trying to get your computer to assess and analyze data and understand it as well, it becomes super important that you provide high quality data so that it knows what are the features, so that you can map the features out and eventually help it to solve the problem. I am sure you guys agree with this on me, right? Well, with this, we can get to one of the discussions wherein, so if we say this is this much important, feature engineering is so important. Did you actually know that data scientists across the world spend majority of their time trying to work on the data rather than work on the solution? Now, you might be very puzzled if you're a person who's new into feature engineering, new into ML, or new into data science, saying, hey, don't you think actual process of writing the algorithm, getting the logic of it, all of that figure out, don't you think that will take time? Is something you might be asking me right now. Well, let me tell you this. You can have the best logic in the world. You can have the most effective, efficient machine learning algorithm ready for data. But if you're not trying to pre-process, clean the data, and maybe understand what features have what impact and later push that out to your machine learning algorithm, it's like, basically tying the machine learning model's legs and asking it to run. It cannot do it effectively, right? So it is something that is well known in our community, that the most important aspect of the working of your machine learning algorithm always lies in the quality, the quantity of the features and the data that you are providing to your model. So of course, a lot of data scientists, data analysts, and experts around the world spend a majority of their time actually trying to understand how they can have their data to its most crisp, to its most concise nature, so that when they provide it to their machine learning algorithm, they are actually 10 steps ahead, in the entire process of efficiency, in the entire process of tweaking and tuning the performance of a machine learning algorithm. So with this, you must ask a question saying, okay, we know what feature engineering is, we understand how important it is in the real world, and of course in the case of machine learning as well. So if the discussion is this, then what is the goal of feature engineering, right? Well, feature engineering not just has one goal to help tweak the performance, but there is one important goal that we have to discuss about. It is to basically align the data to not just make it, work for the solution, but making your data work for the machine learning algorithm as well, right? So making your data compatible. When we say compatible, all we are trying to do is get your data to be understood by the machine learning algorithm in a way where it can use. For example, if you remember, we just actually discussed about one factor, stress, that can also cause diabetes, right? Now, when stress can also cause diabetes, how do you tell your machine learning algorithm what level of stress it is, right? In the casual conversation, we say, hey, I am stressed because of so and so. You never say, hey, I am 30% stressed, or I am 27.5% stressed because of something. We don't say that. It doesn't work like that, right? So in fact, you can find ways to get your machine learning algorithm to understand that. Maybe on a scale of 1 to 5, you can get the person to rate their mental stress daily, and eventually you can figure out a logic. You can actually understand and trace the result, saying, hey, if people are more and more stressed, maybe it causes diabetes as well, right? This is very important to understand. It would have been very easy for you to say, hey, how can we get our computer to know we are stressed or not? We cannot do it, so let's remove that feature. Let's not remove that feature. Let's find out a way in which we can try to use it to our advantage, right? And when your train of thought is like this, you will try to find multiple features. Of course, some of the times the feature might not work at all for your solution, right? It might not be in a way where your machine learning model even understands the data, or you're just trying to take a hunch saying, hey, this may be something, and it might not be at the end of the day, right? So it becomes very important that we understand that this is a very key part of understanding how we can do this. Now, one thing that you guys must be asking yourself right now is, every single time you work with a solution, every single time you work with analyzing what is going on in a data point, or every time you try to find a pattern that is hidden in your data, one thing should always be coming to the top of your mind. It's saying, hey, so data is going to change massively, right? Even if it's in the same solution across different features, it's going to change massively. And if you're talking about multiple solutions wherein you have to find out multiple features for multiple problem statements, don't you think you must have a little bit of expertise, or you must have an understanding of how you can approach feature engineering? In my opinion, feature engineering is considered as an art. Now, I say feature engineering is considered as an art because data is going to be an entity that is going to change at a very rapid pace on a per solution basis. When that is the case, it becomes important for you as a learner and a person who's implementing feature engineering to actually get a sense of direction and to find out if whatever you're doing will help you understand what these features are, how they can very well be used, and in fact even trying to understand what features may or may not break your model as well. Right now, if you guys have worked on machine learning algorithms previously, you can definitely attest to this. You would have been working on a problem statement, it would have been going beautifully well. You add or you remove one feature and that eventually breaks the entire accuracy of your model. It will be a model that is working beautifully at maybe 93% accuracy. The second you remove that feature, or the second you might change something to it that you might think is very irrelevant to it, your model accuracy might just crash down, right? So at the end of the day, having a skill to assess feature engineering is very important, because this part of the entity has such a huge say to even talk about the success or to talk about the failure of a machine learning algorithm. And of course, it's not just machine learning algorithm. This concept of feature engineering trickles down to data analysis, it trickles down to data handling, data pre-processing, machine learning of course, and deep learning as well. In deep learning, we try to get automatic feature extraction and feature selection and all of that, but again, that's a discussion for some other time. But you have to understand it is used there. We use it in all the walks of our lives, as I've given you multiple examples now. It's just that you might have not known it is called as feature engineering. Now that we actually understand that this is the case, okay, so what do we do next? Next, I highly suggest we understand what the process of feature engineering is, to understand how things work. How do you even select a feature? How do you find a feature? How do you understand what happens during the process of machine learning, right? So there are 4 important steps that I want you guys to focus on. It starts out with data selection, then it's data pre-processing, then it's data transformation, and it's data modeling. So let us try to understand each and one of these on a simple level. First of all, when you say data selection, it should be important that you're knowing that, hey, you're trying to collect your data and you're trying to put it into a format that is understood by your machine learning algorithm, correct? Once you've selected the data and once you've made it, brought it to a point where your machine learning algorithm can understand, do you directly just feed it? The answer is no to that, because what happens after you have raw data is for the fact that it'll be not cleaned. It will have many features. It might have so many things which will eventually hurt your model rather than help it, right? So there are some things wherein you'll have to clean it, you have to pre-process it, and you have to make sure that you're sampling your data better to a point where your machine learning algorithm has no doubts about what feature has what sort of an impact, right? So pre-processing becomes very, very, very important in the case of feature engineering. Once your data is selected, once you have pre-processed it ready for your model to use, then what do? Is you transform the data to a point where you are trying to assess and analyze which features have what impact. And when I say transform, you're converting your data from one format maybe to another, and this is where feature engineering comes into the picture. When you're trying to transform something so your model understands something better, well, that is where your feature engineering has a lot to say. Everything right from getting your data all the way to creating your model, understanding why your model's accuracy might be low, tuning your model to make sure it can get better. In all of these places, there is a little bit of say that feature engineering has. But surprisingly, the world is seeing recently, it's not a little say that feature engineering has. In fact, it's a huge say. Previously, when people thought feature engineering is just another thing which might help you get 5% more efficiency, but at the same time, if you have done it wrong or if you have not assessed correct variables, there's a good chance you'll be losing 80% of the accuracy as well, right? So there's a lot to play for, especially with feature engineering. Okay, so we know the process of feature engineering in a brief. So to understand what feature engineering, how feature engineering happens is something you'll be curious about. To answer that question, we need to begin by assessing how we go on to do feature engineering, right? It is basically an iterative process. When we say iterative process, you keep doing it again and again in a loop, right? For all you programmers out there, for loop, while loop is all these iterating statements that you will understand. Until a condition is met, you'll try to do the same thing again and again and again. We have used the concept of iteration in real world as well, right? So maybe you have an aim to run 5 kilometers. Today you run 2, tomorrow you run 3, 3.5, 4, 4.5. So you keep doing it again and again and again till you meet your goal of running 5 kilometers. Similarly here as well, we try to take the entire process of data from data selection all the way to processing, and we eventually break it down into multiple steps wherein we will use one set of data, one set of features to actually perform feature engineering. Later it's a loop. We go back to the data, and once we know what kind of accuracy we got and once we know what we need to tweak and tune, we go back to the data, we eventually tweak or tune that aspect of your machine learning model, and we eventually try to get it to train again, evaluate the performance again, and we keep doing this until our problem is solved. You keep running every single day until you touch 5 kilometers on one very fine day, right? That is literally how feature engineering works as well. We keep doing it in a loop until we actually get to the entire point. Now you might say, hey, isn't this a very inefficient process? We have a lot of data we'll have to process. We'll have to keep retraining your model. You have to keep retweaking your model. And once you tweak your model again, you'll have to train it to check for performance and all of that. Don't you think this becomes a hassle? Is a question you might be asking, but let me tell you this, that entire hassle is worth it because of the fact that feature engineering has such a huge say to eventually tell you, right, about how your machine learning models work. So the process, when we say it's a loop, is basically these 3 steps that you can see on your screen right now. The first step, whenever someone comes to you with a problem statement, should be for you to assess and analyze and say, hey, so these are some of the features that might help us to get to our solution, right? You're brainstorming, you're trying to figure out what are these features, you're trying to understand what are the features that might have an impact, what are some of the features that might not have an impact. If you're considering the same diabetes example we just spoke about, let me give you a different look at it. Now if I say, hey, this person has diabetes because he drives a Mercedes car, and that person does not have diabetes because he or she drives a BMW, right? Now driving a car might have some say on diabetes, I don't know, but when you take a look at the practical aspect of it, it does not, right? So you need to find out what features are important for that solution. So you'll be brainstorming, you'll try to look out for ideas, you'll try to think about the logic of what might cause something. That is step number 1. Once step number 1 is taken care of, the next thing is you'll try to understand if you can find a way to either manually or have some sort of automatic feature extraction from your data. When we say feature extraction from your data, if you're considering the same diabetes example, basically you'll have rows and columns of data. Maybe each column will talk to you about one particular aspect of that patient data, and every row can have multiple patients worth of data, right? So you have some sort of a structure in your data itself, and right now all you have to try to do is figure out which one has what impact. And even before doing that, you'll try to figure out if your model has the capability, if your algorithm has the capability, right? Once it executes, it becomes a model. Until it executes, it's still an algorithm. So you have to first assess, saying, hey, can my model automatically pick up the data in its algorithm stage and eventually figure out features on its own? Yes, there are many algorithms that can eventually do automatic feature selection, and it's a very popular case in the case of deep learning. Now for machine learning, most of the time we do prefer manual feature extraction. If you're working on a very complex example, the first step we usually take is to make sure have automatic feature extraction on, turn it on. It's not a switch that you'll have to turn on. There's a bit of logic, you'll have to work on it. You will basically do it with the automatic features extraction on the first case. See how the model functions. Well, if you have 98% accuracy on your first try itself, you know that it's working out fantastically. Maybe if you have 20%, you'll try to want to revisit it and try to do some things manually, and that where you would implement your own logic and not rely on your algorithm's logic, right? That is step number 2. Once you have brainstormed your features, once you have decided you either want manual or automatic automatic feature extraction, the third step is very simple. You'll try to find out and you'll try to select only those features that are considered to be important for your final result. For example, age, for example, body mass index, for example, fitness, all of these things, right? So you'll find out the importance of features, you'll find out what features to use, you will know how to use them, and eventually you just push all of these to your machine learning model so that it can understand all of that as well. When you look at it on the whole, don't you think that this is a very simple concept yet has such a huge impact on the outcome? Yes, well, considering that as well, you must be curious to understand, okay, so if this is the case, if the level of importance of feature engineering is so high, what are some of the techniques that we can use to make sure we are on top of our game with feature engineering, right? So let us take a look at some of these popular techniques that are present out there. The first most important thing we need to discuss is that there's not just one technique, there are multiple different techniques out there. In fact, there is 5 very important techniques that we're going to be discussing. Everything from data imputation to outlier handling, something called one-hot encoding. Right now, you may or may not know what one-hot encoding is. I have a beautiful example to explain what all of these are. Then we take a look at data grouping, data scaling as well, right? So these are 5 important techniques that we will try to use to understand how we can go on to perform feature engineering in an effective manner. So let's start with data imputation. Now, when you say data imputation, it is always the case that your data is never perfect, right? If your data was perfect, very well tuned, features mapped correctly, and your data completely being correct, as soon as you send it to your machine learning algorithm, of course it should give you a very good accuracy rate considering you've used the right algorithm. This is never the case, is it? We will always have some incorrect data. We will always have some missing values that might be present in a very large data set. If you're talking about 100,000 entries of maybe patient data, there's a very good chance if it was maybe manually done or even if it was automatic, there's something which might have gone wrong. Now, if we have 100 patient data and let's just say 2 patients data are somewhat incorrect or the data does not make sense to the column that is in, right? I'll give you an example. If someone asks you what is your blood group, maybe they fill a form or something, and maybe in the urgency, maybe in that current state of mind, instead of reading it as blood group, they might have read it as mobile number, so they would have entered a mobile number there, and this might have been automatically fed into a scanner or machine or something which would eventually store the blood group as a mobile number incorrectly. Now, when something like this happens, and once you have a lot of data, once you have hundreds of thousands of rows of data like this, there's a very good chance that something can be wrong. On the whole scale, when you take a look at huge amount of data and tiny mistakes, you might say, hey, it's fine. Maybe we will correct it, maybe we won't, and it'll still be okay because every one of us knows that, mobile number is never your blood group, correct? But we know this because we are trained to understand what blood group is. We trained to understand that a mobile number is not a blood group. But as soon as you give this to your machine learning algorithm, it will basically have an outlier, or it will basically tell you, in terms of low efficiency that, hey, it might be learning something wrong. It might be learning something incorrectly. Not because of the fact that the algorithm is not correct, not because of the fact that you have not selected the correct features, but you might have actually done all of these things beautifully, but you've forgotten to handle some missing values in your data, right? It can be for many reasons that this might happen. It can be a human error wherein there's a lot of data entry to be done and 1 or 2 entries might be missed. Or it might so happen that your data was perfectly intact, but while exporting there was a change in formatting or something happened, as in junk values got filled up in empty spaces or they were replaced by zero. Something happened wherein your data is missing, correct? It will come to a case where you'll have to even think about things such as maybe you're trying to send in a lot of data to your machine learning algorithm, but you will not be able to provide some features because of the concerns of privacy. Now, in the diabetes data set case that we're going to be discussing, maybe some people do not want to reveal their actual age, right? It is something that people might not be willing to do. Of course, each and every one of us has our own way of thinking, and some people might think it's wrong for someone else to find out what their age is. It might be offending to people, in fact, sometimes, right? So when they say, hey, I do not want to give my age and I don't want to mention it here, So when you're training that aspect for that patient data on your machine learning algorithm, it will be very confused because it does not have one feature to understand. It doesn't know what age this person might be. So this will not only hurt that person's record, this will not only hurt the accuracy to detect that person's diabetes onset or not, but not having an age there for one person means that it loses one particular point in a checkerboard wherein it cannot figure out that, even though it's a tiny margin, it cannot figure out what age will do for the rest of the people as well, right? It's not like it cannot understand at all. It can, but now that it's one data point less, eventually it will not know that, right? So what would one do when you see incorrect data? What will data imputation? What we usually do is when we have incorrect values, once we have missing values that we know compulsorily that it needs some handling, instead of just deleting the data, right? What we actually do is we replace whatever incorrect data is present with values that have been very common and maybe most frequently used. So when you say blood group, the most common blood group in the world, I think, is O positive. So if you do not know what the blood group of the person is, you cannot find out what it is, or the person does not want to tell you what it is, it's natural for you to assume that, saying, hey, let's just find the most common group and let's just, there's a good probability that person might be of the blood group, so you just put it on there, right? It can be incorrect. The person might be AB positive, AB negative or something, and you've just plonked down O positive there. It might be incorrect, but I'll tell you this, training your model on incorrect data can be slightly better than training your model on missing data, because if you train it on missing data, it will never have a link that it can make. But if you train it on incorrect data, it will still have a link to make, but your accuracy will be low in a way where you can find it out easily, tweak it out, tune it out, be done with it, right? So now you understand one important technique of doing feature engineering is to actually remove certain data, replace it. If you do not have the accurate data to replace it with the most frequent occurring one. Right? This is the first step. In fact, one of the first techniques that I prefer doing whenever I am working on a large data set as well. I try to find out what data is incorrect. You'll have a knack once you keep doing this more and more. You'll have a knack of understanding, saying, hey, this feature might have that much of a say in the model, so let me try to fix everything. And 90% of the time it has worked for me in my favor. So data imputation is something you guys should be considering as well. But data imputation is easier said than done, because there might be so many data points where something is missing, something is incorrect as well. Maybe when someone asks you about, hey, what is your blood pressure, and they have no privacy concerns, and I don't think privacy comes in the way of your doctor and your medical status. So you would probably say, hey doctor, this is my blood pressure, right? 180 over 70, 180 over 90, something like that. What might happen in the case is, maybe when you are trying to get it recorded, or maybe someone is doing a data entry job, they might have added one more zero to it, right? Your blood pressure went from, there's two parts of your blood pressure, systolic and diastolic, right? So maybe one of these numbers is out of whack. Instead of writing 180, someone just entered 1800. Think about it. If the blood pressure is 1800, I don't think the person would be surviving or breathing to even have the conversation with the doctor, right? So in real, yes, the person is fine. It was just an error that was made. But what your machine learning algorithm will see is that, oh, this person has 1800 in their blood pressure. So maybe that is the reason the person has diabetes. So your model will think that, blood pressure is the biggest factor that will cause diabetes. On the contrary, in real life, maybe there is some other feature. Maybe the person is not fit. Maybe the person drinks and eats a lot of sugar, right? Maybe that could be the number one factor. But now that your machine learning algorithm is very confused with the high BP number, it will be like, yes, that is the reason why this person has caused diabetes. Now let me use that learning for the other 10,000 patients as well. You see what is happening? One outlier or a couple of values which you might have never handled, which is incorrect, will basically degrade your entire model's accuracy. And in fact, we have another technique here which will help you resolve all of these things. It's called as outlier handling. It's exactly the reason that I just mentioned, right? Now, what you see in your screen on your screen right now is basically something called as a box plot. A box plot is a statistical concept which will, help us assess and understand many things about our data. For example, what is the most minimum value in the data point? What is the maximum value in the data point? What is the median value? As in, what is the middle value of that range of data? And once we're talking about a range of data, you can cut your data into multiple tiny slices or quartiles, right? So minimum to Q1 is this data that lies here is considered as the first quartile, Q1 to median is the second quartile, median to Q3 is the third quartile, and Q3 to max is the fourth quartile. We've broken the data into 4 parts, quarters, right? So that is the case. But after your maximum values, this is where your majority of your data will lie in this inside box that you see. But there can be certain cases where 1 or 2 cases, or out of 10,000 patient data, maybe 10 patient data wherein some entry was missed, and eventually that person is now that person has 2,500 blood pressure, right? That is an outlier. So once you go on to statistically start plotting everything, once you want to find these relationships, you will realize, hey, this doesn't make sense, this value shouldn't be there. That is when you would go back for doing some more data imputation. That is where you use another technique to handle the outlier, right? First you'll do imputation. Once you're done with imputation, you'll try to see if you can handle all the outliers, right? And once you handle all the outliers, it's an iterative process where it's not just that if you've started with outlier handling, you have to use this. Absolutely not. You have started with data imputation, you came to outlier handling, you realize that there is some other data which is missing or incorrect, so you go back, you do it again. So it's never one technique that is used, it is all of these techniques in conjecture that eventually gives you the fantastic solution you are looking forward to, right? So it's a very simple thing. As soon as you see your data, you will create beautiful looking graphs and visualizations, especially meaningful plots such as these box plots. You will try to see what are some of these outliers, features which are eventually hurting your model's accuracy. Go back, impute it, and eventually try doing this again. Right now, those two are some of the most common straightforward type of techniques that you might handle and you might be working on. But we have one more technique which is super popular in today's world, especially machine learning. This is at the heart of machine learning, right? Now let me give you a quick example of what one-hot encoding is. Now let's just say we need to get our machine learning algorithm to understand that there are 3 teams. Now in this particular case, I have considered the top 3 teams in my opinion for Formula 1 racing, right? Now I'm a huge fan of Formula 1 and I love watching motorsport. So I just thought this example is very nice for you guys to understand. First of all, if you just say, hey, there are 3 Formula 1 teams, Red Bull Racing, Mercedes-Benz and Scuderia Ferrari. If you just say this, now as soon as I look at it, I look at this column here, I look at the data here and I say, oh, okay, so there are 3 teams and these are the 3 teams. Now I understand it. My brain is mapping a million things in the background to know what a Red Bull car looks like, what Mercedes-Benz have done in terms of achievements, what is the heritage of Scuderia Ferrari. All of these my brain is knowing because it has been trained on all of these. As soon as you send a categorical data, when we say categorical data, it's basically the data which you cannot put in the form of numbers. Now, you cannot say Red Bull Racing is 1, 2, 3. We're not trying to find the race outcome. We are trying to assess and get your model to understand that this is a team. Now, once you just send these 3 categorical data, your machine learning algorithm will have no clue what it has to do. Correct? So what you do with one-hot encoding is you take this categorical data, you convert it into numerical data. Now once it's a numerical piece of data, your model can understand it a lot better. How would you do that? Well, here's a very simple example. You can have 3 columns, Red Bull Racing, Mercedes-Benz and Scuderia Ferrari, and eventually you can just have a small matrix which will tell you, hey, if this particular aspect of your matrix is 1, it means that this is Red Bull Racing. You can have another set of rows and columns wherein if this is 1 and these 2 are 0, it means that it's Mercedes, right? And similarly again for Scuderia Ferrari, if you have to say that this driver is a Scuderia Ferrari driver, it means that that person will not be driving for Mercedes or will not be driving for RBR, right? So it will be 0, 0. Now if you understand, your machine learning algorithm can figure out saying, okay, so if I see this kind of a matrix, if I see this kind of a number, I know it is Ferrari. If I see something like this, I know it's Mercedes and I know it's Red Bull Racing. You just took your computer from not absolutely understanding anything about categorical data to breaking it down in a simple sense where it has more clarity about the features right now, which eventually you can use to your advantage. This is one-hot encoding. Now this is very common, very popular, and it's fantastic to a point where it will work on very small data sets at the same capability as it working on extremely large data sets as well. So of course, feature engineering and one-hot encoding go hand in hand, and this has to be one really popular technique that will help you get there. right? So the next technique that we are going to be talking about is data grouping. Now, data grouping is a way to make sure you have more clarity on things as well, right? To give you some clarity, when you were in school or when you were in college, when there was an assembly, we are usually made to stand in groups, right? We were made to maybe stand as per your class, as per a group, as per a team that they would have made or something like that. Why do you think we do this grouping in real life as well? So we have an effective way of addressing maybe more than one entity at the same time. Now when I say, hey, blue team, do this, I'm eventually giving one instruction to maybe 100 people rather than saying, hey, you do this, you do this, you do this, you do this. You get it, right? Similarly, in multiple examples, again, data grouping is something we have always done as a society in the form of making things easier for us. Very popular in schools, colleges, in fact, even in your offices as well, right? You will have multiple teams. You'll have a marketing team. You'll have a sales team. So when someone says, hey, sales team, do this, they're addressing a multi-audience there, right? So similarly here, we will group our data so your algorithm can understand things better. This is a very popular feature engineering technique wherein we will, group the data in the form of two things, right? We have two types of data. If I go back, you will see on your left, this is all categorical data, which is again not numerical. On the right, you will see data which was categorical data but now is numerical data, right? It's ones and zeros. Your computer can understand that. So for data grouping, you'll have to split it out here to say, okay, how can we group all the numerical data that are out there? How can we group all the categorical data that are out there, right? So to group numerical data, again, another example. If you basically ran 1 kilometer today, 2 tomorrow, 3 day after, and 4 and 5, you took 5 days to hit 5 kilometers. You can find out what is the average you ran totally, right? 1 plus 2 plus 3 plus 4 plus 5 divided by 5. That is simply giving you the mean. That is simply giving you an average of what you ran every day, right? Now, when you think about doing it this way, once you find out, hey, I ran an average of so and so over so many days to basically touch my goal. That is grouping in its very simple sense of numerical data sets, right? You can sum up your data to group them. You can find the average of it. You can find the median. You can find the mode. The mode basically talks about how many times the data might have, reoccurred. So today you ran 1 kilometer. Tomorrow you ran 2. For the next 10 days, you ran only 2 kilometers a day. So if you ask me what is the mode is going to be 2 because that is the maximum occurrence of whatever you're talking about in the event, right? So that is numerical data grouping. And if you're talking about categorical data grouping, this is where one handy function comes into the picture. We call it as the lambda function. Lambda function will add concrete meaning to your categorical variables in a way where transformation occurs. And once your data sets, once your grouped data starts transforming, you will try to figure out new ways of how you can handle that data, and eventually the function will provide a condition. The function will provide a path, I want to say a structured path to help your data to be handled as well, right? So data grouping is again another very important technique in feature engineering. Now, it's not only that, as we discussed, there are many ways you can handle it. In fact, here is one more feature engineering technique. It is called as data scaling. Now, whenever we are trying to work with certain data, it might be that we'll have a range to work with, right? So I'll give you an example. Let us consider that you're trying to find out the age of some person, or you're trying to get your machine learning algorithm to predict the age of this person. When this is the case, don't you think age, we have a range? Your age can never be minus 10, minus 5, minus 1. To be very honest, I don't think it can even stay at 0 probably, or definitely not below 0, right? And if you're talking about human age, it cannot go above 100, 110, very rare cases above that as well, right? So you have a working range, 0 to 100, let's just say, or most popularly 0 to 80, 0 to 85, something like that, right? So you have a range to work with your data. Now, what happens with you scaling your data and bringing it to symmetry is saying that, hey, if someone mistyped instead of 80 to be 800, that will not be an outlier, and eventually your data is being squished down to a workable range, right? So if your data is, if someone entered 800 instead of 80 there, that's a red flag. That is either you keep the data, you kick it out, or eventually you understand that with imputation, you would rather fill it with the most common, the average age of everyone, for example, rather than, I say, kicking it out. When I mean removing it, you wouldn't want to do that, right? So Again, multiple techniques in conjunction with this, and we have a very popular term for this whenever we are trying to bring anything to a range. It's called as normalization. Now, for the people who might have worked with probability, you will realize that the probability of occurrence of something might be between 0 and 1. There is probability is never negative. Probability cannot be above 1, right? Because it's like a percentage. 10% of probability, 100% of probability, 99.95% of probability. Correct? So this is where if you have a probability of 1.5, it doesn't make any sense, right? So you have a range saying it has to be 0 to 1, and no matter where it is, just squish them down, bring them to this kind of a range, right? That is where data scaling comes into the picture. But if you are trying to squish your data out of its proportion, what will happen is it will increase your outliers, right? You just took 800 and brought it down to 80, or maybe you just took 85 and you realized that it's not correct, and you eventually went completely to the other end of the limit and you made 85 to 100. You just added 15 years of life, 15 years of life to that person's age, and it might be an outlier because your machine learning model will be like, oh, this person is 100 years old, so there has to be diabetes, right? Everything you do, it will try to learn to a good amount of depth wherein it might analyze it and assess it wrong, and your accuracy can go down. So what we do is, once we start scaling up our data or scaling down the data, the first step you have to keep in mind is to make sure you understand that it will create a lot of outliers. But this is not a big headache as well. Once you have a lot of outliers, you can eventually handle these outliers, remove the values, impute them, do whatever it is required, and once that is done, you eventually go back and you normalize and you bring it to the range, make sure that nothing else goes wrong, and you're done with that, right? So normalization, data scaling, data handling, imputation, one-hot encoding, these are some of the really popular concepts that eventually govern how the entire world of feature engineering works and what sort of an impact it has further ahead as well, right? Alright guys, so to talk to you about what a correlation matrix looks like, why it is required, and how we actually go on to use it, you have to first of all look at it and see if you can find some patterns into it and understand what it means, right? Now, the most important thing that you really have to know about a correlation matrix is that we use it to make sure we can determine some relationships that exist between independent and dependent variables, right? Now, when I spoke about the diabetes example for you guys, I gave you a hint of saying, hey, blood pressure might cause diabetes, blood pressure might be related to your age, your body mass index might be related to, the sugar intake that you might have, all of those things, right? So what we need to assess and figure out is there a way that we can say that blood pressure is maybe 30% important in understanding its relationship with age, or maybe something like insulin does not have anything to do with age, something like that, right? So all of these answers, all of these questions, when you're actually asking, you can find out the answers because you have one entire chart which will give you relationship between multiple variables that are figured out, right? Now I'm sure that you would have seen the fonts on the left and the bottom might be very small for you guys to read it, and the numbers on the right. In fact, this is the exact correlation matrix that we are going to be taking a look at in the demo that I told you guys. So when we get to that point, we will make sure to analyze and assess not only what it is. Now we understand what it is. We'll take a look at how we can read a correlation matrix. Can we have positive and negative correlation and all of that? So we're gonna have a discussion on this in the section where we're gonna do this practically, because then I can walk you through it as and when we're doing the demo, and you'll have a better understanding of the same. Alright, now that we have taken care of correlation matrix, the next thing that we're gonna have to take a look at is the concept of underfitting and overfitting. Now I am very sure if you're a person who's into data science, analytics, or who's into machine learning as well, these two terms are gonna be the ones which are thrown around like confetti, right? Why is it so important? What is underfitting? What is overfitting? Why does everyone sort of put this as the prime importance factor no matter what when you talk about feature engineering? Is it really that important? We're gonna answer all of that, right? Now, underfitting and overfitting are these situations, are these conditions that you wouldn't want to find yourself in, or you wouldn't want your machine learning algorithm to find itself in. If you do not handle overfitting and the concept of underfitting, guess what happens? Your model accuracy is going to tank. It's going to not just fall. When I say model accuracy falls, I may be talking about 15%, 20%. When I say it tanks, it's going to go from 90% accuracy all the way to 50, 40% accuracy, and eventually that will occur, right? So handling the concept of underfitting and overfitting, even before you know it, one thing you have to get across to your mind right now is, yes, if there is underfitting, if there's overfitting, how do I find it out? What is it? How do I remove it? Those are the three questions you guys must be asking yourself. If you do not handle underfitting and overfitting, as I'll be explaining going ahead, you will figure out on your own saying, hey, this is not possible for my model to understand. This is how it's trying to learn, right? So let's try to separate this out in simple terms. Let's try to understand underfitting first. Next, let's try to attack what overfitting is. Underfitting basically means that there is low amount of variance in your data and it shows a very high bias value. What does this mean in a non-technical term? In a non-technical term, this means that there is an insufficient amount of data points that your model can use to train, right? If your data does not even allow enough modeling wherein you can have functions to be fit into those data points, if there is no sufficient data points for your function to sit and work on and give you a predictable result, what do you think is going to happen? Efficiency is going to go down, correct? So what you should be after is, when you're looking at underfitting, is to provide more data points, right? It's like saying, it's very simple. If I say, hey, I need 25 grams of carbohydrates to maybe run 10 kilometers, but if I give you only 5, can you run? There's a good chance I'm going to say no to that particular question, because it might not be possible at all. You will run out of energy, right? If you have a 3-volt battery that you're trying to pull 12 volts out of, does it work? No. Similarly here as well, if you're providing insufficient amount of data, your machine learning algorithm will never be able to connect the dots and eventually run functions on these data points and eventually give you a workable result. This underfitting is again as bad as you think it is, right? If you don't have data points to train the model, your model is not able to figure out or make sense of anything that's present. It's not able to learn enough. Do you think it can work well? No, right? So similarly, we have overfitting now. Overfitting is a situation wherein your function, where your model has so much data to learn. It has so much data wherein it has to run a function which is very closely fit into a very small amount of data points. What does this happen? You're overtraining with a large amount of training points and your model will be very, very complex at the end of the day. So learning little is very bad. Learning way too much is also very bad, because here we cause a very high variance values and eventually a low bias value. And if you're a person who knows variance and biases, you will know that either of the outcome with respect to underfitting and either of the outcome with respect to low overfitting will not work. That is not a case which will lead to an efficient model. You guys agree? Well, yes. So how do you understand overfitting and underfitting better? On the technical term, underfitting is something as simple as not having enough data points for your model to train, so it will not train well, it will not work. For overfitting, it is saying that there is a lot of data points which is fit into a limited amount of data point space with respect to function mapping, so it's doing way too much than what it's supposed to, so it's not doing it well. Technically, that is the case. But to help you guys understand underfitting and overfitting, let us take a look at a very simple situation wherein you are the person. Let's just say you are the machine learning algorithm today, and you are trying to, just like how we were kids and we used to watch cartoons where there's a pirate ship that comes onto an island and they start digging where the X mark is and they try to find the treasure there, right? So how does the situation talk about underfitting and overfitting? With respect to underfitting, if you are not digging enough, if you know where the treasure is, you know that maybe it is 50 feet into the ground, you'll have to dig the sand for 50 feet, right? So you're just trying to dig a little, you get tired and eventually you say, no, this is not possible. I have dug so much, the treasure is not there, I will leave. right? This is underfitting, when your model cannot train so much longer, it cannot train on more data points to a place where it never finds patterns. Another example in the same situation is you will never know where to dig on the entire island as well. That is also underfitting, right? If you don't know where to dig, if you don't know how much to dig, and if you just try a little and say not possible, well, your model won't work as expected. Underfitting. Now let's talk about overfitting. Overfitting is when you know, saying, hey, this is where the X mark is, I know that is where the treasure is, so let me start digging very aggressively, very quickly, to a point where you would have maybe made a small mistake and you would have dug around the treasure. If your treasure is here, that you're trying to dig from the top, you eventually come here and you go around and you go down. You're missing that entire treasure point, because you're digging so aggressively, you're digging so fast, you're digging in a lunatic pace, I want to say, and you're missing the entire point of even reaching the treasure. This is overfitting. When you're working so much, you're stressed, you have a lot of strain, you're not able to keep up your efficiency to a point where when you're digging, everything else apart from the treasure, it's just noise, it's just useless information. You're there for the treasure, but all you're finding is more sand and rocks and everything which you never wanted to find. That happens in the case of overfitting. When your model is trying to hunt so much in depth that it is finding more noise than useful information. That is the case of overfitting. With underfitting, you're not doing enough. With overfitting, you're doing it so much that eventually the entire point, the exercise, the goal is not being met, right? So this is something which is very important that you guys had to understand about. And now that we know what is feature engineering, how it is used, where it is used, how does it work with machine learning, what is the goal, what is the importance of it, and we eventually even figured out the various ways of you can achieve feature engineering with the many techniques. We took a look at understanding the process. So now we have a complete picture even with correlation matrices, right? So right now it is high time we actually dive right into Python and we start for taking a very simple use case. In our case, it's going to be the same diabetes prediction using machine learning, where we will talk about every single step and understand where feature engineering comes into the picture. And very importantly, we are going to understand how you guys can read a heat map, or you guys can read the correlation matrix as well, right? So let's just jump right into Google Colab. Google Colab is nothing but a very simple Jupyter notebook hosted on the Google Cloud platform. It's just like any other Python IDE and Jupyter notebook out there. So let me quickly open it up and we can get started by looking at Python code and eventually solving our diabetes example, the diabetes problem statement that we eventually discussed at the start of this session, right? Superb. Let's get into it. Alright guys, so I just opened up Google Colab. I already have a Jupyter notebook with the code pre-written for you guys to make sure that we can actually spend time analyzing the code rather than writing it out manually. So let me zoom in so that we understand what we're doing here. First of all, we are trying to get a machine learning algorithm to predict if it can find if a person has diabetes or not. Now, how is it doing this? It is doing this by assessing and analyzing the various features that we are providing it, saying, hey, if this person has this amount of, maybe blood pressure, if the person has this amount of BMI, there are many other things that we can also take a look at to see if they cause diabetes or not. Now, how do we know for sure if the person has diabetes or not? Is we already have the data. We know the outcome. Now, as soon as I show you the data set, you get better clarity on that. So let's just first begin by trying to import all the libraries that we're going to be using, right? Since we're writing the code, in Python, we're going to use libraries such as NumPy, Pandas for basically numerical computation and having the access to the Pandas data frame, data structure. We're going to be taking a look at using Seaborn and Matplotlib. These are absolutely fantastic data visualization libraries. In fact, the top data visualization libraries for Python in the world today. We're going to be, taking a look at scikit-learn, or sklearn as it's called. sklearn is nothing but scikit-learn. It is a very important aspect of using machine learning for your Python code. Right now, as soon as I execute this, all it's trying to do is it's trying to import all these libraries, so I don't have to call it again and again and use it again and again, right? Very simple. Now, the step where we are actually trying to take a look at the data set, we need to bring it to our working environment. Right now, if I just hit play, it'll have absolutely no idea where the data is, because Google Colab is running on the Google Cloud platform. The data set is sitting in my computer here. So I'm going to go to file, I'm going to hit upload. As I'm just going to go to data, I'm going to go to files, data sets. I have the diabetes data set here. I'm going to hit OK, and I'm going to see that it is actually uploading, and it is uploaded. Now when I run it again, this time it will not give me an error because it knows that there is the diabetes data set at hand, right? So I have just told you about the data set. I think it's high time we actually take a look at understanding what the data elements of the data sets are. So this is what the data set looks like. Now if you think that, hey, you only have 5 rows of data, well, that's because of the fact that I've just printed out 5 for you. You can we'll find out the total number of rows and columns in our data set as well, right? Just to keep it very crisp and concise, we've printed out only the first 5 patients' data. Now it's very simple. Every single row that you see, right, this row is one patient's worth of data. Every column that you see is a feature that we are trying to talk about. Now in this particular case, you can see that this particular patient had a glucose level of 148, the other one had 85, 183, 137, 89. So these are each individual people who have these glucose values, blood pressure values, skin thickness. So even skin thickness has a very important thing to do with diabetes. Maybe the onset of the person being pregnant or not might also have a say in diabetes. You have something called as body mass index that we just took a look at, right? If it's somewhere around 25, it means you're fit. If it's above I think it's 28 or 29, that means you're absolutely obese. If it's below that, it means you might be malnutritioned or something like that, right? So you have something called as age as well. We discussed the age. When you talk about the age, you have to also think about how the age might have a say on the outcome, and we have the actual outcome itself. Now if the outcome is 1, this means this person, this entire detailed person here, this data of the person means this person is diabetic. If it is 0, it means this person is not diabetic. So we already know for a fact that the person might or might not have diabetes. What we are going to do is we're going to just remove this last column. We're going to completely separate it out, and we're going to just feed everything else to the machine learning algorithm and get it to understand if it can predict it correctly or not. Once it has made its learning, we are going to eventually test it with the outcomes to say, hey, can you figure out if this person has it or not? There is one more train of thought that you can think about is manually you can take a look at and find if a person has diabetes or not. Now this person has very high glucose rate, a little bit blood pressure is also very high, skin thickness is high, BMI is very, very high. So this person is obese, right? Now when that is the case, I can make a guess looking at this saying, if this is the trend, this person may be diabetic. Let me scroll to the right. There's a very good chance this person is diabetic, right? Now I know this. Getting our machine learning model to just figure out whatever I have said, that is what we are trying to achieve here, right? So there are various columns that are out there, everything from the values of pregnancy, the number of times the person was pregnant, the glucose value, blood pressure value, skin thickness value, insulin, body mass index, age, outcome. All of these things have a certain say in the final outcome itself, right? So these all of these data will have a certain amount of say in having the outcome. For example, I just showed you, right? If your BMI was very high, I thought the person is going to be diabetic, and it turns out he or she was, right? That is important. So let's take a look at the data set in itself and find out how many patients worth of data do we have. I just printed out 5 for you, and here it indicates that we have 9 total columns first of all, out of which outcome you can remove for now. Apart from that, we have 786 patients worth of data at our hand, right? So quickly taking a statistical look at the data set, you will figure out the average values. For example, taking a look at the count value tells you how many rows of data do you have. So we have 768 patients worth of data, and each of these have 768 in them, which means that there are no missing values. Very, very important, right? And then if you take a look at all the 768 data, what is the average pregnancies that everyone, the entire data set is giving out? It's somewhere around 4 kids. It cannot be 3.8, it has to be 4, or it can be something around 3, right? So the average glucose is 120. 70, average BP is 69, average skin thickness, average BMI is very, very high, right? 31.99. But that I cannot just say looking at this average BMI and that say everyone has high BMI. No, some of them might have very low BMI, some of them might have absolutely high BMI, which is causing this kind of a shift. But on an average, I can take a look at it and I can have outcome clarity on it, right? You can find out standard deviation, you can find the minimum value, 25th percentile, 50th percentile, 75th percentile, and the maximum value as well. Right? Superb. You remember I told you about how important pre-processing is, but in my case, it will not be important because the data that I have is already pre-processed and cleaned enough for the machine learning algorithm to work. So what I'm going to do is I'm going to ask the ML algorithm if there's any NaN values that are present in the entire data set. Now, NaN stands for not a number. Now, if I ask you what is your glucose level in your body or what is your blood pressure, and if someone tells me, hey, my blood pressure is O positive, will it make sense? No. So that's exactly what we're trying to catch here. If there is any mistyping, if there's any error that's happening, since it says false for everything, I can be assured that since all of these have to be numbers, all of them are numbers, right? So they can, to one level of extent, you can say your data is correct. Now the next thing is where we're going to actually try to understand the correlation that exists between each of these labels, right? This is the matrix that I wanted to talk to you guys about, correlation matrix. Here, first of all, what you see on the right side, these numbers are nothing but legend values. If your color is somewhere around that, it means that your value will be somewhere around that, right? Now, if I just take this black color, if I just scroll here and find black, I know that black is somewhere around 0. So maybe the correlation here is 0. Now, if I bring it up, basically as light as it gets, there is more and more and more correlation. That's interesting because the lightest color you can see here is white and every diagonal element is white. Why is that the case? That is the case because you're trying to compare the exact same thing with the exact same thing. Now, if I try to compare pregnancies with pregnancies, it is exactly the same thing. So it's going to be 100% the same. That's the reason it has very high correlation. Glucose with glucose. Similarly, every element on the diagonal is comparing itself. So you can literally remove all of these elements because it doesn't make sense. If I compare BP with BP, it will always say that this is 100% the same, 100% equal and all of that, right? Okay, now that we know how to basically read correlation matrix, let me take one example out here. Now, if I have to find out the relationship that exists between insulin and maybe skin thickness, right? Look at this, insulin is here, skin thickness is here. I see that this color is very light in color. It's a pinkish color, right? Now, I try to match this color here. I think there is somewhere around 0.5 correlation between skin thickness and insulin. But what is this 0.5 correlation in between that? Well, what we are trying to assess is to find the find all these variables which have some sort of a dependency or a relationship, right? At the end of the day, there are some independent variables, there are some dependent variables. When you try to put a map saying, hey, this might be the case, right? I'll give you a very simple example. Here we are only talking about positive correlation, like how one can have a positive impact on the other. There are cases where there's negative correlation also, right? Now, a very quick example for negative correlation can be something like think about the amount of fuel you'll have in your fuel tank, and as soon as you ride, your fuel goes down but your distance goes up, right? You can drive more if you have more fuel, but at the end of the day, if you compare how much fuel you started out with versus how much fuel you have in your tank, of course your fuel is going down but your distance is going up. You see, it's negative. Simple, right? So here in our case, we do not have anything as such. We have nothing to say that blood pressure will automatically come down with age. We cannot say that, right? So absolutely, we are only considering positive correlation in our case, but negative correlation does exist, and I hope you understand that by now. Superb. It's a very simple thing, guys. You will find out how much of a relation one variable has on the other variable and how much of it has an impact on the outcome itself, right? So if you're trying to just look at all of these variables and quickly make an assessment, glucose is 0.466, almost 0.5, right? So I can say that in the entire amount of features that we are taking with respect to how the glucose varies and affects our outcome, it is it has a correlation of 0.5 almost, as in there's a 50% chance that if a person has a high glucose value, the outcome is that he or she may be diabetic, right? I didn't have to perform machine learning. I looked at the correlation matrix and I could figure something like this out. Now what we're going to do is, we know that there are 768 people in total, but how many of them have no diabetes? I can tell you this because I have the data. If I just scroll to my data, move to the right, I know what the outcome is. Look at this. I know if this person has diabetes or not. I know if this person has diabetes or not. Similarly, for 768 people, I know this. So all I have to do is find out who all have outcome 1, and that's the people who have diabetes. Outcome is 0 means they don't have diabetes. So all I'm trying to do is give you a sum to tell you that these many people have no diabetes. Let me zoom in a little. Right? So in this particular case, 500 people out of the 768 do not have diabetes. So of course that means that 260 odd people, 268 people have diabetes, right? Now just looking at these might get a little confusing. So let's actually quickly print a count plot with the use of Seaborn to show you this in a graphical manner, right? Now outcome is 0. If it is 0, it doesn't mean this person has diabetes. If the outcome is 1, it means this person does not have diabetes. Now on the y-axis we have count. So since this is bigger, I can say that, hey, 500 people have no diabetes, somewhere around 250 or 260 people have diabetes. This is another quick way. Instead of writing all of this code, you can quickly find out who has diabetes, who doesn't, right? Great. Now what do we do next? Once we have all the data ingested, ready, pre-processed, cleaned, and we know our features, we know the independent variables, we know dependent variables, everything is done. The next thing that we are going to do is we're going to just remove the outcome. We're going to drop that entire column, because that is our target variable. That is what we are trying to get our machine learning algorithm to predict. So we're going to drop all of that, and we're going to divide the entire data set into two things. One is the training data set, the other one is the testing data set. With the training data set, what we are trying to do is we are actually giving it this data to the machine learning algorithm model to learn. Now once it learns, we're going to have some other data which it has never seen before that we are going to use to test its accuracy. A very simple example is you guys using your textbooks to learn for your examination, and eventually you are asked a question in the examination. If you have the textbook right next to you, you can copy and it won't make sense. It's not an examination at all. But what if you are asked to keep your textbook outside, find out what the answer is, find out how much you have learned using your knowledge, and write a test? That is exactly what we're doing. So 80% of my entire data is going to teach the particular model. 20% of it I'm going to keep it for later, wherein I'm going to be testing. So all I'm doing is that I'm dropping the outcome variable, I'm splitting the data to 80% training, 20% testing. Now I can say it's 20% because the test size here is 0.2. If it is 0.3, it means 30%. If it is 0.4, it means the test size is 40%. And regardless, as soon as you set one, since it has to total to 100, the other one is very easy to calculate. Now what I'm doing next is to actually use logistic regression to perform model fitting and get the model to learn with respect to what data is happening. Now for all the people who might be confused saying, hey, isn't machine learning a very long process? Don't you have to write hundreds of lines? Well, actually, no. This one line calls which algorithm that I want to use. This one line talks about basically the process of model fitting, talks about it using the data. And with these two lines, it has actually run its maximum iteration, as you can say. Number of iterations is reached. It's a small warning. It is fine. So with this, our machine learning model has already trained. It took a couple of milliseconds and it's done. The next thing is I have to give it some sort of testing data to eventually get it to understand if it has learned something or not. So I gave it a little test now. After the test is given, what I'll do is I'll print something called as a confusion matrix. Now for all the people who do not know a confusion matrix, this matrix will, I can just take a look at this matrix and I don't have to look at any other piece of code. And I can tell you if your model has been performing well or not, because these four numbers actually talk about true positives, true negative, false positive and false negative values, through which you can say, hey, this is the actual case. This person actually has diabetes. So did your model predict that this person has diabetes or not? If it is a yes, then one of the true positive values will go up. If it is no, it means your model predicted it incorrectly, right? So you can find out how many incorrect instances did it catch, how many correct instances did it figure out, and overall you can find an accuracy accuracy score as well, right? So I know that some of you all might not be able to read a confusion matrix, so let's just go on to print an accuracy score for this particular model. Now the accuracy score in my opinion should be somewhere around 75%. It is 74.6%. So what this is telling us is, for every 100 patient data that you feed into your machine learning algorithm, the model can guess 75 of it absolutely correctly, and the other 25 it might struggle a little. Now there are many ways that we can go on to. Maybe we have new features we need to train, maybe have some other dependencies in these variables, maybe something we are missing, but at the end of the day, this is nothing but a 20-25 line piece of code that is eventually doing everything from taking your data all the way to giving you a staggering 75% accuracy, and to tell that, hey, I as a machine learning model can give you exact accurate result for 75 patients out of 100 patients. I think with limited training and with respect to a data set which has not been processed in depth, and maybe there are many other factors as well, this is a fantastic result, right? So you have to understand this. Even though you might think that a feature may or may not have anything to do with it, the second you try to figure out correlation, the second you try to feed this correlation to your model and get it to train in a rapid fashion and give you an output, you will realize that this is very, very important for the vital working of this model. And at the same time, a feature that you have thought which has nothing to do with your model might end up being the one that has the most say in your result, right? So all in all, in whole, this very simple logistic regression demo that we have, wherein we discussed multiple ways of how you can use multiple features, understand correlation, and quickly build a model and to rapidly take it from prototype to actual working model. I think you should have a complete picture now that, hey, with respect to feature engineering, there are again so many things to explore, so many processes to take a look at, and eventually start using them, right? Alright guys, so to summarize the entire course, we started this one out by understanding what feature engineering is. We have used feature engineering in many walks of our life, but we just didn't know it was feature engineering, right? So we had an introduction to it, we understand where it is used, how it is used, why it is so important, what is the goal of it, and we also took a look at the entire process of how feature engineering can be achieved. Once we took a look at that, we also made sure to understand the various techniques that we can go on to use, and I explained each of these techniques in a simple manner, I hope. And after we took a look at that, we made sure to cover bases on overfitting and underfitting, because that affects, even though you might have really great features, at the end of the day, if you have not handled overfitting and underfitting, that will crash your model's accuracy. So we also made sure to learn about that. We took a look at understanding what correlation is, positive correlation, negative correlation with respect to examples. We understood how to read the chart, and of course we had an entire machine learning demo wherein we saw that, hey, these features can have this amount of correlation, and at the end of the day, we got somewhere around 75% accuracy for a very simple model, which at the end of the day should give you complete clarity on what feature engineering is, how it is used, and this should serve as a foundation going ahead, so that you can build upon this and understand everything that you've taken away from this particular video and start working on new features, different ways of thinking, multiple ways of handling that, right? So guys, I hope everything we've covered in this particular course is clear to all of you all. On that note, I wish you all the very best for your learning ahead. My name is Anirudh Rao, and I'll see you in the next one.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.